Hello, and welcome to this presentation, Understanding Duplexers. In this presentation, we'll provide a short technical introduction to duplexers, how they're used, and the most important measurements made on duplexers. This presentation assumes a very basic knowledge of S parameters and a very basic knowledge of filter measurements. If you're unfamiliar with these topics, or if you'd like a brief review, you might want to watch the presentations Understanding S parameters and/or Understanding filter measurements before beginning this presentation. Duplexers are 3-port RF devices that enable a single antenna to be used simultaneously for transmitting and receiving. Duplexers are used when the frequency separation between transmit and receive is small, typically on the order of hundreds of kilohertz to low tens of megahertz, and this is a common situation in radio repeater systems. Note that the two user ports of a duplexer are often designated as high and low, but it's possible for the offset between transmit and receive to be either positive or negative. Duplexers have two primary design goals. The first is isolation or attenuation between the transmit and receive frequencies, and this is usually at least 70 to 90 dB. The other requirement is low loss between the user port and the antenna at that port's pass frequency. Less than about 1.5 dB is desirable. In addition, a duplexer may also provide protection to external receivers or protection from external transmitters. In the remainder of this presentation, we'll go into more detail about how duplexers are constructed, tuned, and measured. We'll start with duplexer construction. All duplexers are constructed using filters. These may be bandpass filters, which pass the frequency on each port, and/or they may be band reject or notch filters, which block the frequency of the other port. Cascading filters, that is, using more than one filter type in series, can improve filter performance. This is particularly important when transmit and receive frequencies are close together. Most duplexers use tunable cavity filters, but other types of filters, such as ceramic or comb line filters, can also be used. These other types of filters are, however, less common in duplexers, due to limitations with regards to power handling, performance, cost, etc. Multi-cavity duplexers come in a variety of form factors, shapes, and sizes. Some of the more common ones are illustrated here. All duplexers have 3 RF connectors, one for the low side frequency, one for the high side frequency, and one for the antenna connection, also sometimes called the common connection. Almost all duplexers contain at least one band reject or notch filter, whose primary purpose is keeping the transmit frequency out of the receiver, since this can prevent receiver overload and/or descents. For example, a band reject filter on the receive side is tuned to notch out the transmit frequency, but pass the receive frequency. A secondary purpose of a band reject filter is to keep the receive frequency out of the transmit port. This is primarily to avoid intermodulation or mixing of the transmit and receive signals. Note that it's not uncommon for a duplexer to have multiple band reject filters in series to provide additional attenuation. It's also worth noting that many inexpensive duplexers are often made exclusively using notch filters. There are, however, disadvantages to a duplexer built only from band reject filters, mostly due to the fact that these types of duplexers will pass all signals except for the notched transmit or receive frequencies. This is acceptable in a relatively uncrowded RF environment, where there are no other nearby transmitters or receivers. By nearby, we mean both close in frequency as well as close in physical distance. If other strong external signals are nearby, these will be passed through a notch-only duplexer and can create the same type of issues we mentioned on the previous slide, namely descents and the creation of intermodulation products. Another disadvantage of a notch-only filter is that, on the transmit side, imperfections in our transmitted signals, such as harmonics, spurs, etc., will pass through unattenuated and may cause interference to other nearby spectrum users. Duplexers, therefore, often also incorporate bandpass filters that pass the transmit or receive frequency at their respective ports. These filters are designed to pass the port frequency with minimum attenuation, but provide some degree of attenuation at all other frequencies. There are several reasons why this is desirable. First, it prevents external signals from entering the transmit and receive ports. This reduces the risk of descents on the receive side and intermodulation on the transmit side. As mentioned earlier, a bandpass filter on the transmit port also helps to protect other external devices from any spectral impurities, such as harmonics, in our transmit signals. In other words, the transmit bandpass filter helps our system to be a good neighbor. Like band reject or notch filters, bandpass filters can be connected in series to improve performance. Note, however, that it's difficult to obtain high out-of-band rejection using only bandpass filters. This would require cascading additional filters and/or larger filters. The rejection in bandpass filters used in duplexers is often many tens of dB less than the rejection obtainable using a notch filter, and thus it's somewhat uncommon to find a duplexer that's made up only of bandpass filters. Therefore, many duplexers consist of a set of bandpass and band reject filters, both in the transmit path and in the receive path. These two paths are then connected to a shared antenna. Recall that the band reject or notch filters are primarily designed to prevent self-interference, especially descents of our receiver from our transmitter, and the bandpass filters are used to limit interference to, or from, nearby external devices. Although constructing duplexers from a combination of both bandpass and band reject filters is very common, the number of each type of filter and their order in the signal chain will vary between duplexer designs. Before we move on to measurements, let's take a few moments to talk about duplexer tuning. Duplexer filters, both bandpass and band reject, must be tuned to match the system's transmit and receive frequencies. This is done by the user during installation. For the cavity filters commonly used in duplexers, tuning is most often performed by changing the length of the rod or plunger in the center of the cavity. Let's look at a notch or band reject filter. Generally speaking, pulling the rod out of the cavity will raise the resonant frequency of the cavity, and pushing the rod in will lower the resonant frequency. Filter tuning is a complex topic and is often described as more of an art than a science, so we won't be covering filter tuning in detail in this presentation. But in most cases, the cavity filters used in duplexers are tuned individually, and then additional fine-tuning is performed once the filters are connected in series. Measuring or characterizing duplexers is most often done using a vector network analyzer, but in some cases, measurements can also be made using a spectrum analyzer with a tracking generator. Because of the high level of rejection provided by duplexer notch filters, the instruments used to measure duplexers normally require a high dynamic range. A fast sweep time is desirable when tuning filters, so the effect of a tuning adjustment can be seen in near real time. Most duplexer measurements are made pairwise, or between two ports at a time. Unused ports should be appropriately terminated. And as with other network measurements, calibration should be performed to improve accuracy as well as to remove the influence of the test setup, such as connectors, cables, etc. There are three basic types of duplexer measurements: attenuation between the low and high side ports and the antenna port, the isolation between the low and high ports, and the standing wave ratio or return loss seen at each user port. We'll start by looking at attenuation. Attenuation is measured between either the low and high port and the antenna port. In network analyzer terms, this is an S21 measurement. As mentioned earlier, the unused port should be terminated. The most important goals of this measurement are verifying that the band reject or notch frequency on one port matches the frequency of the other port, as well as verifying that the notch has sufficient attenuation, typically 70 to 100 dB. We'll look at several examples of this on the next few slides. Another duplexer characteristic that can be derived from this measurement is insertion loss at the port's own frequency. Normally, this will be a couple of dB or less. For duplexers which incorporate a bandpass filter, the passband frequency and attenuation can also be verified in this way. The passband should be centered around the port's frequency, and there should be at least moderate attenuation, low tens of dB, outside of the passband. Let's look at an attenuation measurement on a band reject-only duplexer. This duplexer has transmit on the low port at 145 MHz and receive on the high port at 145.6 MHz. If we measure attenuation between the RX port and the antenna, we see a large notch at the transmit frequency. Recall that this helps prevent descents of the receiver. Similarly, if we measure between the transmit port and the antenna, we see a notch at the receive frequency. It's worth noting that in this example, the notch in the transmit path is substantially deeper than the notch in the receive path. Since we're usually more concerned with descents of the receive port, rather than intermod at the transmit port, it would actually be better to switch the low and high side frequencies, if possible, when using this duplexer. Next, we'll look at a duplexer that uses both band reject and band pass filters. Here, the transmit frequency is 955 MHz, and the receive frequency is 960 MHz. Measuring from the RX port to the antenna port, we again see a deep notch at the transmit frequency. But we also see a band pass response at the receive frequency. Signals at the receive frequency have only minimal attenuation or insertion loss, but signals outside of this range are moderately attenuated. For example, a signal appearing at 985 MHz would be attenuated by about 15 dB before it reached the receive port. A similar shape and behavior can be seen in the transmit to antenna path as well. Note that in each path, the notch and bandpass are at opposite frequencies. Let's look at one last example of a combined band reject, band pass duplexer. Here, the separation between transmit and receive is much higher, about 22 MHz. We see the same combination of a band pass response and a notch both in the receive path and in the transmit path. Note that compared to the previous duplexer example, the bandpass response is much flatter and more symmetrical outside of the passband, but the amount of attenuation outside of the passband is relatively minor, only about 5 dB. And as we saw in our first example, the notch depths are not the same in both paths. This is actually not uncommon in many duplexers. The next measurement we'll look at is isolation, which is the amount of attenuation between the low and high ports. Like port-to-antenna attenuation, this is also an S21 measurement. And as before, the unused port, here the antenna port, should be terminated. Ideally, no signals would pass directly between the high and low ports. That is, there would be infinite attenuation between them. But in practice, port-to-port isolation will be highest at the notch frequencies of each port, and will be significant at frequencies outside of these notches as well. Isolation can be measured in both directions, but transmit to receive is usually the most important measurement, since we're most concerned with keeping transmit power out of our receiver. In most cases, however, isolation measurements will be roughly the same in both directions. Let's look at an example isolation measurement. Here we're making an S21 measurement from the transmit or low port to the receive or high port. As expected, we see the greatest isolation at each port's notch frequency, almost 100 dB in the transmit frequency and almost 120 dB at the receive frequency. But even outside of these frequency notches, the isolation is still quite good. Within the measured frequency range, the minimum port-to-port isolation is about 30 dB at the point halfway between transmit and receive. The last measurement is standing wave ratio, SWR, or return loss. This is the amount of power reflected by either the low port or the high port, and hence in VNA terms is an S11 measurement, in which power is sourced by the instrument, and the amount of return power at that same port is measured. As before, the unused port should be terminated. Ideally, signals at the nominal port frequency would see a good impedance match with minimal reflected power. Measurement results are plotted as a function of frequency, either as standing wave ratio or as return loss. It's very easy to convert between these two units if necessary. Typical duplexer values are a return loss of 20 to 30 dB, which corresponds to a standing wave ratio of less than 1.2. Keep in mind that this may also be somewhat different between the low and high ports. Here we see an example of a return loss measurement made on the transmit port of our duplexer, which has been tuned for a nominal transmit frequency of 464 MHz. As we would expect, there is very high return loss and very low SWR at this frequency, meaning that a transmit signal at 464 MHz would see a very good impedance match with very little reflected power. Elsewhere, the level of return loss is very low. This means that most of the incoming power is reflected at these frequencies, and thus standing wave ratio would also be very high. Before we end this presentation, let's briefly explain the difference between duplexers and diplexers. These words are sometimes used, incorrectly, as if they were interchangeable, and even some duplexer manufacturers have been known to do this as well. This is a somewhat understandable mistake because, like duplexers, diplexers are also three-port devices that combine low and high-frequency signals onto a single common port. However, diplexers are used to separate or combine widely spaced frequency ranges or bands. By widely spaced, we mean the bands are tens to hundreds of megahertz apart. This is done using only high-pass, low-pass, or bandpass filters, not the notch filters commonly used in duplexers. Another difference is that the filters in diplexers are often constructed using inductors or capacitors, rather than the cavity filters we see in duplexers. And finally, diplexers are generally fixed and cannot be configured or tuned by the user, whereas duplexers often require tuning of both their band reject and band pass sections. Please see the separate presentation, Understanding Diplexers, if you'd like to learn more about diplexers, how they're used, and how they're measured. Let's end with a brief summary. Duplexers are three-port RF devices that allow the simultaneous use of closely spaced transmit and receive frequencies on a single antenna. This is very common in radio repeater systems. The primary function of a duplexer is to prevent the transmit signal from getting into the receive path, since this could easily lead to desense or even damage of the receiver. Duplexers are, however, also helpful in avoiding issues with intermodulation and/or interference. Duplexers are constructed as a series of band pass and/or band reject filters. In most cases, these are tunable cavity filters, and multiple filters may be cascaded together to improve performance. Duplexer frequencies must be adjusted to match transmit and receive in a given system, and therefore require tuning. This is most often done with a vector network analyzer or a spectrum analyzer plus tracking generator. Common measurements made on duplexers include the amount of attenuation at the notch frequency and passband, insertion loss, isolation, and SWR. This concludes our presentation, Understanding Duplexers. If you'd like to learn more about other radio frequency devices, how these are measured, or about test and measurement instruments from Rohde and Schwarz, please see the links in the video description. Thanks for watching. Please subscribe to our YouTube channel and visit us at rohde-schwarz.com.